Hello everyone, welcome back to Alkaline Hydroxide 784. Actually, I'm re-recording the audio because after 5 minutes I realized I was just saying random stuff and I didn't make much sense, so I'm just gonna start again. Okay, so today in the physics series we are doing temperature and ideal gases. I'm just gonna follow the learning outcomes and try to explain it to the best of my ability. But if you find it confusing or anything, just say it in the comments below so that I'll try not to be confusing. Okay. Yeah, so the first one is about two objects in thermal equilibrium. So the example that I provided was the idea of some coffee and some air in a closed space like a box or something. And the coffee is at 90 degrees Celsius and the air is at 20 degrees Celsius. So after some time, if you assume that there's no heat transfer to the environment, like outside the box, it's within the box only, the only place the thermal energy can actually go, as in the thermal energy in the coffee or the air, they can only be in either the coffee or the air, in a sense. You get what I mean, right? So over time the thermal energy will then equilibrate in a sense, so it will spread out evenly in such a way that the coffee and the air will have a thermal equilibrium in a sense. So what does that mean? Well, in a sense, even though the coffee and the air are made of different things, since temperature is quite a unique property, so it's quite a unique, what do I call it? Unique property, and it doesn't, like, just because the coffee has a different heat capacity from the air doesn't mean that the coffee will then be at 50 degrees and the air will be at 40 degrees. That's just not possible for the thermal energy, because thermal energy will keep moving until the two regions have an equal so-called density of thermal energy, as in yeah, like with regards to their heat capacities in a sense. So yeah, so they're in thermal equilibrium after some time. And because of that, when you stick a thermometer into the air, you will get the same temperature. If you stick a thermometer into the coffee, you get the same temperature. So the temperature is pretty much just like a proportional value to the thermal energy in the coffee and the air. It is not really it's not defined by the other properties of the coffee or the air. And that's why two objects that are in thermal equilibrium have the same temperature. And in fact, this is how thermometers work. So, yeah, this isn't mentioned in the learning outcomes very overtly. So so the idea, this particular idea is it the zero law or is it of thermodynamics? The idea is that if A and B are of the same temperature and A and C are of the same temperature, then B and C will be of the same temperature. Thermal equilibrium or thermal equilibrium, anything works, I think. They both mean this means the same thing anyway, so that's the idea. And so if you use a thermometer and you touch it on a surface that's 20 degrees Celsius, and then you take the thermometer, go to another location, and then you touch it to another surface which says 20 degrees Celsius, then you know that those two places are both 20 degrees Celsius, no matter what. You for sure know that because the thermometer was 20 degrees Celsius in both cases. So it was in thermal equilibrium with each of those cases. And that's why you need to wait for some time for the mercury or whatever thing that they use in thermometers nowadays to rise up to a particular temperature, because it is undergoing thermal equilibrium. But if you want to be super technical about it, maybe you can say, oh wait, but once you remove the thermometer, it's taking some of the thermal energy with it and all that stuff. But since the thermometer will be like a small surface area, like compared to the big surface area from the object that you're measuring, it should be almost the same, if not the same temperature. So that's how thermometers work. Okay, cool. Now let's move to the other part of, like, the other thing which involves temperature scales. Okay, so I'll just look through the learning outcome and then and insert related info on the scales accordingly. So the second point is about the gas laws and absolute thermodynamic scale in the sense. So for the gas laws, we imagine it in terms of um, usually we imagine it in terms of ideal gases. So first of all, you have a gas, and if you if you heat it up, like you increase its temperature, then you can witness that the gas expands. So that in a way the temperature is proportional to the volume, because that's what they've observed, and that's what they've theorized. And the other thing that we found out is that if you constrain the gas in a particular container and it cannot expand, what happens instead is the pressure increases. So temperature is proportional to pressure as well. And that's how you have pressure and volume put together in one side of the ideal gas law, PV. And on the other side you have T. So what is the proportionality constant here? We are assuming that all of the gas is having the same amount of molecules at any point of time, so same amount of substance, like so n is the same, and r is another constant that has been calculated from evidence and things like that, so experiments and things like that. So that's how you get PV equals to nRT, as well as the other gas laws that come to define PV equals to nRT. I mean, there's a way to use the gas laws and then um, have a hypothetical scenario, and then you write down each of the laws, and then you combine them together to get PV equals nRT. So how you do that is, for example, you have P is proportional to T, and then V is proportional to T, and then P is proportional to 1 over V. So let's say you start with a gas of PVT. Those are the parameters. And then you say that, oh, if you you then change the temperature to T2. So if you change it to T2 but the volume is kept the same, then you now get P2V T2. And then from there you can say, oh, it's if you change the what else you change the you change the volume, then it becomes you change the volume but you don't change the temperature, then it becomes P3 V2 T2. And then from there, if you do some maths, then you can get the gas law somehow. Like you have to make things the P1 P2 the subject, and then you do some minusing off, and then from there you will get your proportionality like the you find out that there's a proportionality constant, and then you can get the PV equals nRT equation kind of. So that's how you do get the gas laws. I'm sorry, my nose is like a bit blocked and it's like making me sound weird, so just deal with it. So what's the absolute scale of temperature? uh what I mean, we have Celsius. Celsius is based on the water melting and boiling point, which is 0 and 100 degrees Celsius. So that's Celsius. And we have Fahrenheit, which is based on the melting and boiling point of brine water, which is 0 degrees Fahrenheit and 100 degrees Fahrenheit. Yeah, really, that's what it's based on. So, but as you can see, this is based on a property. It's based on the melting point of water, boiling point of water. But if you go to different places, the melting point of water can be different. So, it's not really the most, even though it's pretty accurate for most scenarios, because you're not going to be doing your experiment on a mountain. Let's say if you really wanted a super accurate and for always consistent scale, you would want something that isn't dependent on a certain property of water in a sense. And in fact, there are many other constants that were once dependent on a certain property of carbon. Carbon 12. Is it a certain property or something? There's like one property that they were dependent on, and then they changed the definition to make sure that to define it in a way that is not dependent on a property. and therefore it was always consistent no matter what. The mass and everything was all changed accordingly, and that is really a big thing. So, oh yeah, so not nothing to do with carbon per se. I think that's in the new definition. And the old definition of 1 kg was based on a particular mass that they had in France or somewhere. They just had this mass sitting there doing nothing, and they said that this mass is exactly 1 kg. But do you think it's gonna really stay as 1 kg? It could accumulate dust or something and then suddenly become 1.000001 kg. Then is 1 kg now 1.000001 kg? It changed it's not a good thing, right? You cannot expect all of the weights in the world to suddenly all of the weight that people calculate, like the mass per se, to suddenly be a different value. So likewise, temperature, you would want it to be based on something that isn't a physical property that can just change at any point of time. So for the kg, what they did was that they associated it with stuff that involved the most fundamental stuff, like uh the neutron, proton, yeah, like basically atomic stuff. So it's a bit more consistent now. It's not going to change so easily when it involves stuff like that, compared to a 1 kg piece of metal just sitting somewhere in France. Okay, so for temperature, what they did instead was to find a scale called the Kelvin scale. I mean, not they, but more of a guy called Kelvin found the Kelvin scale. Yeah, like how a guy called Celsius found the Celsius scale and a guy called Fahrenheit found the Fahrenheit scale. And there's even some other scales, so yeah, it's the Rakhine scale or something. I'm pretty sure that's one. That one is kind of like the Fahrenheit scale, but it's a bit different value or something. Like how Celsius is like a translation of the Kelvin scale. The Fahrenheit scale is a translation of Rakhine scale. Yeah. Anyway, that's not important. So what is the Kelvin scale based on then, if it's not based on the melting point of water? Um, it is based on, well, it's just based on the most basic fundamental way that thermal energy works, in a sense. So if you have any molecule, and we'll find out the equation later, and if it's vibrating, it is consistent for each and every molecule that exists in the world. So based on the temperature that it is at, and the thermal energy that it has, it will vibrate at a certain velocity or with a certain amount of energy, and that is what is proportional to the Kelvin scale temperature. And that's why we have something called absolute zero, um, which is 0 K, and that at that particular temperature, the internal energy or the thermal energy that the object has is zero point zero point, like just zero. There's no absolutely nothing that can change that zero to 0.1 suddenly. You know what I mean? Yeah, unless you add thermal energy to it, and therefore it is consistent. It won't change even if you go to the top of the mountain, have different pressure, different don't know what. It will still be zero, and that's why you can measure the temperature of the space. Like the universe, basically the outer space temperature. You can measure that, and you can find the temperature of other planets without having to assume the same pressure conditions as Earth, in the sense. So what is this? What can we tag the Kelvin scale to? Well, basically, it's based on the triple point of water. So the triple point of water is actually pretty consistent. It's very consistent because it it is based on a very particular um, it's based on a particular pressure and temperature and volume, and like the condition is very specified. It's not like melting point of water, you didn't really specify the pressure. I mean, you assume that it's atmospheric pressure, but it can change, right? They didn't really specify that, oh, it must be this particular pressure that it's at. but here they'll specify everything, and therefore the value cannot change. So yeah, so at triple point it is 0.0 like 0.16 degrees Celsius, and that is two 273 Kelvin. Is it? 273.1. Sorry. It's 273.16 Kelvin and it's 0.01 degrees Celsius. Sorry, yeah, 0.01 degrees Celsius. So that is a triple point of water. So yeah, you can just look it up. You'll see the graph. Anyway, that's just how it works. So how do you convert from Kelvin to Celsius? I think we already know the answer. You just add to, if you have the temperature in Celsius, you just add 273.15 to that value and you get the temperature in Kelvin. Yeah, so please remember the 1.15 because that is more accurate than saying 273. Even though you might have used 273 in secondary school, you must use 273.15 in A levels and even in uni, possibly. Or not, I don't know. Depends on how strict your teachers will be in uni about that. Okay. So now let's move on to the actual important equation called PV equals nRT. Yep, the ideal gas law. Of course, you do realize that this is based on ideal gas. uh, yeah. So the ideal gas, there's a lot of conditions. It's like the basic assumption of the kinetic theory of gas. Likewise, I think the same assumptions would apply to ideal gas. So we'll look at the assumptions later, but first I'll tell a bit more about the equation. So what is PV equals to nRT? P is the pressure, V is the volume, N is the mole, the amount, R is 8.31, or it could be 0.0821 based on the units that you're following, and T is in kelvins, so please remember that, temperature in Kelvin. So if you're using 8.31, I believe that you would need to do what's the unit that you need to follow for this? I always keep forgetting what are the units I need for this particular value of R. Okay, so if you go to your data list, right, you can see that R is stated as 8.31 joule per Kelvin per mole. So you know that is the unit here is joule. If you can ignore Kelvin and mole because that's covered by the N and the T, so that's not the issue here. So the P times V has to equals to something that is in joules. So how do you achieve that using SI units? Yeah. So if you have well, joules is energy, so joules would be like force time, yeah, like force times distance or something. Okay, if you imagine it that way, so the unit of joules will be like Newton meter, and then Newton will be like what kg meter per second squared. So the joule SI unit version would be kg meter square per second square. So how do you get that in your pressure and your volume? You use SI units, like you basically use meter cube for volume, and for pressure you use Pascal. So Pascal is for SI units. If you use APM, it won't be SI units. So yeah, use Pascals. So Pascals is defined as Newton per meter square. Yeah, Newton per meter square. And then if you have meter cube, then you times it by meter 3 times, and then you get Newton meters. Yeah, wait, what? Newton meter. Okay. Okay, never mind. I don't know what I just said, but you get the idea. You use Pascal and meter cube. That's what will work. Simple as that. Okay, so now, okay, so joule is Newton per Newton meter, right? Yeah, so if you will get Newton meter if you times Pascal and meter cube. Okay, simple as that. So that's how you remember the units to use for pressure and volume. That's all I had wanted to say for that point. I'm so sorry. So you can just use this liberally in your questions once you say using the assuming ideality of the gas or assuming that it's an ideal gas. Then you can just happily say, oh, PV equals to nRT, blah, 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 blah. Okay. Yeah, you get the idea. It's pretty simple. Just use a calculator, find the value, remember the units, and write down whatever thing you need to find out. Okay, so now let's move on to something that you should definitely be knowing right now. You know what N is? It is referring to the amount of stuff, right? The amount of substance. So it is represented in moles. That's the unit of N. And what is 1 mole of a substance? Well, 1 mole means that there is 6.02 times 10 to the power 23 particles of that substance. So let's say you have oxygen and you have 6.02 times 10 to the power 23 oxygen molecules, then you have 1 mole of oxygen. And this number 6.02 times 10 to the power 23 is called the Avogadro number. Oh my gosh. Oh my gosh. So Avogadro number, which honestly, I'm pretty sure you have said avocado at least once. It sounds so much like avocado. Yeah, I know, right? I mean, if that helps you remember, then just use that. But please don't write avocado in your exam paper. Please use the right spelling. Okay, I mean, you don't need to spell it, so it's not very important. So just remember the number 6.02 times 10 to the power 23. Yeah, if avocados help you remember it, then use that. That helps you. Fine, go ahead. Okay, so yeah, so the number is stated as 6.02 times 10 to the power 3 per mole. It's written in your data booklet, so don't worry. I mean, you don't need to memorize the number, just know that this is what it is. Okay, so finally we get to the assumptions of the kinetic theory of gases. So in assumption, we are looking at ideal gas, kind of, because otherwise it may be slightly different from what we are looking at. So the first thing that we are looking at is that the gas molecules are moving in constant random motion. Yeah, I'm pretty sure you would remember this, even if you do not remember everything else, you remember this for sure. Because you've heard this like 10 times, 10,000 times already, then it's literally there in your head. Even after A levels, it will be there in your head. And what is this referring to? There's a Brownian motion, right? Like you see like dust particles moving around somehow. It looks like they're magically moving around, but it's actually the air molecules in constant random motion moving these dust particles around. So yeah, just use that to remember your constant random motion, or maybe you don't even need anything to help you remember that. Okay, so your molecules are moving randomly and constantly. Good. That's the first assumption. The second assumption is that the molecules have minimal attraction, intermolecular attraction. So what does that mean? In chemistry, yeah, chemistry. I'm pretty sure you need to know these things for chemistry as well. So, you know, this is one topic that you can study for 2 subjects. Isn't that great? You can study one topic and then use it for 2 subjects. Yeah, okay, never mind. So in chemistry, you have many different kinds of molecules. You have polar molecules, you have non-polar molecules, and you'll have different interactions with each other. And let's say if your oxygen, okay, let's say if you have water vapor, you know that water vapor will have hydrogen bonds with other water vapor molecules. So technically, it doesn't really, it has intermolecular attractions. But here we are assuming that there isn't any because intermolecular attractions can affect our so-called theory that we're coming up with here. That's why we assume that there is minimal intermolecular attraction. And to make that even more truthful, to make it even more certain, we would say that the molecules are the space that the molecules take up is negligible compared to the container. So you imagine that there's very little molecules within that one container. Yeah, or at least the space that the molecules themselves take up is very small compared to the volume in the container. And the reason why they say this is because it helps to minimize your intermolecular attractions, and it also helps to minimize the effect of the molecule actually having a measurement or space to it. Yeah. And yeah, what else? I know there's like seven. How many have I said? Three. Oh no. Yeah, never mind. Okay, so oh yeah, elastic collisions. We covered elastic collisions in one of the topics. Yeah, so another assumption is that the molecules always undergo elastic collisions with the wall or with other molecules. So in an elastic collision, the energy is just transferred between the molecules, or and when it collides with a container, the energy is just makes the molecule go in the opposite direction. So in a way that, and it doesn't affect the overall energy of the system in a sense. Uh, and then what else? I told four. There's three more. But yeah, if you can remember these four, then you'll be okay lah. You may probably need to say three or four maximum, so don't worry. Uh, it was the other three. I can't remember. Oh my gosh. Yeah, this just requires like some memorization is required. So the four that I said are easy to remember if you understand this well, but the other three I think is a bit harder to remember unless I'm forgetting super simple things that would have been easier for you to remember. In fact, I don't know. Anyways, so you get the idea. So there's seven different assumptions, and you can get this in your notes as well. So just read your notes. So yeah, just read your notes for the information. So the next point is the what is this? Oh yeah, you're deriving the formula now. So how do you derive the formula? It's a whole process of its own. It's a whole process. So we start with, I'm sorry for that. Something fell down. Okay, so we'll start with a box. We imagine that this box is a cube. It's not some other shape, it's just a cube. And the cube has equal lengths on all the sides because it's a cube. And we'll say that this length is some unit, like a unit length in a sense, so it's easy for us to follow. Okay, so we'll just call this length x, okay? X. And then we will then get a bunch of gas molecules inside it, and we assume that they follow all of these basic assumptions. Okay, so so happens is that we know that the gas molecules will be constantly moving around and colliding with the wall. So if you look at one gas molecule and we think of the speed of the molecule, so we first say that it starts from, like, you can technically start from any point, but the most simplified way of looking at it is like it starts from the wall, then it moves to the other wall, hits the other wall, and then comes back to this wall. So it has a certain speed, right? So the speed would then be 2x over the time taken for the ball, not the ball, the molecule to go from this end to that end to this end again, which would be a distance of 2x. So likewise you can do the same for all the directions in a sense. Imagine the y direction and the z direction. Yeah. So if we look at the x direction, right, the well the speed from each of these molecules can be averaged in a sense. If and the way that we average it here is by squaring it and taking the average of the square, because that's somewhat more efficient than just averaging it directly. So if you imagine that each molecule has a speed of c in the x direction, so you call it 1, 2, 3, 4, 5, 6, 7, 8, like you C1, C2, C3, C4, C5, C6. And you don't need to know the exact value of all of these speeds. So you just state that, oh, okay, um, you know, if you know how to write it, like the two pointy thing, the more than less than sign thingy, and then you put the c x squared in the center, and then you say that, okay, see this, what is it called, the mean of the square of the wait, what, sorry, the mean of the square of the speed, oh yeah, the square root of the, I don't know what I'm doing right now. Okay, sorry, the mean of the square of all of the speeds is equals to cx squared in these two signs, okay? And then since we know that there's three different directions that we are considering, three different axes, we can then say that the speed from each of them contributes 1/3 of the speed to the overall average of the square speed in the sense, and therefore you get 1/3 c squared, okay? And if you want to get the speed, you just square root this c squared in the sense. Yeah, so then from there, what are we trying to find out? Okay, we know there's 1/3 c squared. If you want to find kinetic energy, you will get what? Half mc squared, right? Half mc squared. If you want to get internal energy, on the other hand, well, I don't know. Internal energy is kinetic energy plus potential energy, kind of. Yeah. But if you wanted to extend this to PV equals to nRT, we we know that this this particular energy is proportional to T in a way. And so let's say your half mc squared is proportional to T. And since PV is proportional to T as well, then your C squared will be proportional to PV. Yeah. And from there, and the reason why you can actually put the 1/3 there instead of putting 1/2 or something like that is because we can use the n, n in amount. You can then get the number of molecules from there, and using the mass of the molecules, mass of one molecule as well. So the mass of one molecule times the number of molecules is the mass of all of the molecules. So how do you get the mass basically? Volume or density. Yeah, mass or volume is density. That's one way of looking at it. If you want to look at moles, you can be like mole times the molecular mass of the molecules, like of the substance. That's how you get the same value, I guess. Yeah, actually, I don't know what I'm talking about. I think, okay, I'm just gonna tell you that I might write it out better. So just read whatever I've written down so far, and then you figure it out. It's a bit hard for me to tell it out because my train of thought isn't very good unless I write it down. It's easier for me to think when I write down things, so I'm not actually writing it down now. I'm only writing it down in the video, so yeah, hopefully I would have figured it out there. So you can derive the relationship PV equals to 1/3 nmc squared from this whole process. And we know that the kinetic energy is half mc squared, and we know that it's proportional to temperature because we just I told you that the thermal energy is like this intrinsic this special property that doesn't really, that's based on the movement of the okay, I didn't tell you, but it's based on the movement of particles. Like, so the kinetic energy that the particles have actually contribute to the temperature, and that's how you get your thermal energy from the particles moving and hitting things, you get thermal energy. Yeah, so from here you can get half mc squared equals to 3 over 2 kt, and that's a equation that you can use for questions. I'm pretty sure you probably won't get that much chance of explaining the model, so don't worry too much about that. So if yeah, we come to the end of this topic, I believe. So if there's any other questions, please leave them in the comments below. Good luck for all of your exams. If you enjoyed or found this video useful, please press the like button and subscribe. And with that, I would like to say thank you and bye.